All right, in this video, this is the start of 2 days. We're going to be taking a second look at how we can graph functions, this time using the information the derivative and second derivative supply. So I want you to copy down this fascinating graph, and I'm going to fill some stuff in underneath it. Pause, copy, play. Okay, so here we have the graph of a function f. And today we're going to be looking for some key things about this graph. We're going to want to try and figure out on what intervals is the function increasing. So like I see, it looks like from -infinity to 2, and maybe from 5 to 8, the graph is increasing. And on what intervals is the graph decreasing? So maybe from 2 to 5 and from 8 on to infinity, right? So I'm going to throw down some information about increasing and decreasing. We'll see some interesting things. All right, so from here until 2, we have that f is increasing, right? That means the slope of f is positive. So i.e. f has positive slope. Okay? Now, we know how to determine the slope of f, and that's with the derivative. So we could say, i.e., the derivative of f is greater than 0 on this interval. Okay? So the key take home is, if we want to know where f is increasing, I can just try and calculate where the derivative of f is positive. Similarly, if I go over here, from 8 to infinity, f is decreasing. Okay? Well, that means the slope of f is negative. So i.e. f has negative slope. All right? And again, we know how to find the slope via the derivative. So i.e. f prime of x is less than infinity. Sorry, is less than 0. It's negative on this interval. All right, so the take home here is f decreasing is the same as when f prime is negative. All right? Okay, now I want you to observe something interesting. We've also got a stretch where we're decreasing here and a stretch where we're increasing here, but I don't want to cloud up the things down here, right? But what's interesting is if I go from increasing to decreasing or decreasing to increasing, if I look, interesting things happen when I switch from increasing to decreasing or decreasing to increasing. So right here at 2, the graph is switching from an increasing graph to a decreasing graph. And right here, what's interesting is the derivative, f prime of 2, slope of the graph, slope of the tangent line, is equal to 0, right? And right down here at 5, where we go from decreasing to increasing, I note that the tangent line slope, or the slope of the graph, is also 0, all right? Okay, well, now at 8, we go from increasing to decreasing. Something strange happens up here as well. We have this sharpness, okay? So if you're sharp, no matter how much you zoom in on the graph at that spot, it's still going to be sharp. It's never going to look like a nice flat line or line at all, okay? It's always going to look like it's sharp. And what this means is that the derivative at this spot, 8, does not exist, okay? So I can go from increasing to decreasing by having a sharp turn, which means the derivative is not defined, okay? I'll also just point out that here at maybe 10, the derivative also looks to be 0. It looks like I've got a horizontal tangent line there, but I'm not going from decreasing to increasing or increasing to decreasing. I'm going from decreasing to decreasing, which is a bit weird, okay? But please observe, when I do flip from increasing to decreasing or decreasing to increasing, it looks like my derivative is either equal to 0 or it does not exist. But it's possible to have a derivative equal to 0 where we don't switch behaviors from decreasing to increasing or vice versa, right? Right, so if I want to know where are we increasing, I'm going to look for where my derivative is greater than 0. And if I'd like to know where is my graph decreasing, I'm going to look for where the derivative of the function is less than 0. And I seem to change behaviors when my derivative is 0 or not defined, though it's not a foolproof system, okay? All right. So we're going to spend 2 days on this, and our first day's goal is to simply find where the function is increasing, or intervals on which the function is increasing, intervals where the function is decreasing, local maximums, which I'll define, and local minimums, okay? So why don't you pause, copy this down, and then press play. All right, so the key insight from that last panel is sort of twofold. Increasing means a positive derivative, decreasing means a negative derivative. And if the function is continuous, so if I can graph it without lifting my pen from the whiteboard, if it's continuous, then the graph switches from increasing to decreasing or decreasing to increasing at special spots. Let me just call one of them x equals a. And what's special about x equals a is one of the following two things has to occur. The derivative at a is 0, or the derivative at a is not defined. It does not exist, okay? Now, if I find a spot A where either of these two behaviors happens, I'm going to say that x equals a is a critical value of f. Something unusual is happening there, right? Cool. All right, so now I'm going to do 2 examples where I basically sketch the graph using this derivative information to figure out increasing and decreasing, right? All right, so here's our first example. Why don't you copy this down and copy down the steps that I'm going to follow in order to sketch a graph of this function. All right, so my process. To get the sketch of it, I'm going to try and aim for where are we increasing, where are we decreasing, where do we switch, right? So the first step is going to be to find all the critical values. That's going to require me to take the derivative, figure out where it's 0, or figure out where it's undefined. Once I have those critical values, I'm going to figure out the intervals where f is increasing and the intervals where it's decreasing, okay? I'm then going to plot the critical values, and I can then classify them as to whether they're a local maximum or a local minimum, and I'll explain what that means. And then I'll sketch the graph. I could add in more details like find the y-intercept, find the x-intercept, and we will, but let me just do this very basic stuff first. Okay. All right, so step 1. I'm going to take my derivative and find the critical values. All right, so the derivative, we're getting good at this. Derivative of x to the 4th is 4x cubed minus, for x cubed, the 3 comes down, hits the 4, and becomes a 12. And the new power is an x squared. So it was a 3x squared, and the 3 hit the 4 to get a 12. And there's a plus. The 2 comes down, so I have 2x to the first, but the 2 hits the 4 and becomes an 8. All right? So there's my derivative, 4x cubed minus 12x squared plus 8x. And I'm going to sort of ask 2 questions. Where does this equal 0? And where is this not defined? Okay? All right, well, let me first simplify it a little bit, and then I'll try and solve those 2 things. So I noticed that everybody has an x in common and a 4. So I could factor out a 4x, and that would leave me with an x squared minus a 3x plus a 2. And then x squared minus 3x plus 2 also factors. So I think I get an x minus 2 and an x minus 1 equals 0 and equals does not exist, okay? All right, so let me take care of the does not exist one first. What I'm looking for is there an x value that makes a denominator 0 or that gives me a negative under a square root or under an even root. I see no denominators that are 0 and I see no roots. So I don't see any problems plugging any x value into here. I mean, look, it's a polynomial. Its domain is all reals. Polynomials are great that way. So I don't have to worry about an x value making the derivative not equal to 0. And that was where I would get a sharp bend in my graph. Okay? All right, so if I just set it equal to 0, I can just set each part equal to 0. So I get the x values of 0, x equals 1, and x equals 2 if I put them in increasing order. So these are my critical values. These are the only places the graph can switch from increasing to decreasing or decreasing to increasing, okay? Those changes in the graph only happen at critical values, right? Okay, well now I'm going to use those critical values to figure out what the graph is doing, okay? So step 2, I'm going to find the intervals where we're increasing and decreasing. And what I'll do is I'll take the critical values and put them on a number line. 0, 1, 2. So these are the places where the graph of f could switch from increasing to decreasing or vice versa. Now, on the intervals in between these critical values, the graph of f can't switch from increasing to decreasing or decreasing to increasing, right? Because the only places we can switch are these critical values, right? What that means is the intervals in between and surrounding the critical values, my function is always increasing on an interval or it's always decreasing on an interval. Never does anything else, okay? So I'm going to test each interval now, all right? So let me test this first interval. And here's how I'm going to test. I want to know, what's my derivative sign? Is my derivative positive or negative here? If the derivative is positive, the function f is increasing. If the derivative is negative, the function f is decreasing. So I'm just going to grab any x value I like in that interval and plug that number into my first derivative. So -1's in that interval, so let me plug -1 in. I've got my derivative down here, all right? Any of these versions of my derivative is fine. I'll use this last one. If I plug in x equals -1, 4 times -1 would be negative, -1 minus 2 would be negative, and -1 minus 1 would be negative. So to have a negative times a negative times a negative. So that's 3 negatives. So it's a negative number. I don't care what the number is, just whether my derivative is positive or negative. So if I plug in x equals -1, I get a negative times a negative times a negative. So that's definitely negative. F is decreasing on this interval, okay? Then I'm going to repeat the process. Between 0 and 1, I'm going to take a number like a half, any value I like between 0 and 1, can't use 0 or 1, but something in between, and give it to your derivative and ask, is my derivative positive or negative? So if I give x equals a half, that would be positive, that would be negative, and that would be negative if I plug in x equals a half. So I have a positive times a negative times a negative. So that's a positive times 2 negatives is positive. So f is increasing on this interval, okay? Go to the next one. So between 1 and 2, I could do like 1.5 or 3 halves. Grab a number in between, doesn't have to be halfway, anywhere in the like. 4 times 3 halves is positive, 3 halves minus 2 is negative, 3 halves minus 1 is positive. So to have a positive times a positive, that's negative. So f is decreasing. And last but not least, after 2, I could just plug in something like 3. And if I plug in x equals 3, I have a 4 times 3 is positive, 3 minus 2 is positive, 3 minus 1 is positive. So I have 3 positives multiplied together. That's positive. So f is increasing. Okay. All right. So I can now tell you the intervals were increasing and decreasing. So f is increasing on, well, this interval from 0 to 1. So 0, 1, and this interval after 2. So 2 to infinity. And f is decreasing on, well, before 0, so that'd be negative infinity to 0. And what, from 1 to 2, we're decreasing? So I've answered the question of when f is increasing and when it's decreasing, on what intervals, and there it is. Okay. All right, let's plot the critical points, right? I've got 3 critical points, and I can plot them. So I'm going to do a little table. So this is step 3, little table. To plot them, I need to plug them back into my original function, x to the 4th minus 4x cubed plus 4x squared. 0, 1, 2. So if I plug in 0, you can go through this slowly if you like, but if I plug in 0, I get 0. If I plug in 1, I get 1. And if I plug in 2, I get 2, 4, 8, 16. 16 plus 16 is 32, 2, 4, 8, minus 32, I get 0 again, okay? All right, and now let me start to sketch the graph out, and I can then say whether we've got some local maximums, local minimums, or neither, okay? All right, so I'm going to erase this part and sketch in my graph. All right, so this is a pretty compact graph, it appears. I'm going to plot my critical points first. So I have 0, 0. I have 1, 1. And I have 2, 0. Those are my 3 critical points. And now I'm going to throw in my increasing, decrease, and increasing behavior, okay? So in this first interval, f was decreasing, so I'm expecting the graph to head down. The second interval, f was increasing, so I'm expecting the graph to head up. Third interval, we're decreasing, and the fourth interval, we're increasing, okay? Now I just have to take that shape and bring it down to here. So I'm decreasing until I get to x equals 0. And at x equals 0, the derivative was equal to 0, so I'm sort of thinking I'm rounding that up, okay? Then I'm increasing until I get to 1. That's what this bit's saying. And at 1, f prime of 1 was equal to 0. The derivative of the critical points was 0 in this case. So I've got a nice flat behavior at 1. And then I'm decreasing until I get to 2. And after 2, I'm increasing. All right, and at 2, the derivative was 0 again, so I need to sort of flatten that thing out, okay? All right, so there is, roughly speaking, the graph of f, okay? All right, so one last example, sort of run through the same process with this slightly more unusual graph. Okay, so why don't you pause, copy this thing down, go through it. Like to sketch the graph of g of t. All right, so first off, I'm going to try and find my critical values. So critical values. So I need to take the derivative and find out where it's 0 or undefined, okay? Now, to take the derivative, it's probably more useful to write this as t to the 2/3 minus 4, okay? All right, so let's take the derivative. G prime of t equals, well, t to the 2/3 derivative would be 2/3 t. 2/3 minus 1 would be negative 1/3 minus 0, okay? All right, so there's my derivative. I'm going to simplify it just to make it look a little prettier. I've got a 2, I've got a 3 in the denominator, and I've got a t in the denominator since it had a negative power, and the 1/3 means a cubed root of t, okay? Now, to find the critical values, I need to either set this thing equal to 0 or find where it does not exist, okay? All right, now the only way a fraction can equal 0 is when the numerator equals 0, but the numerator is always 2. So I don't think this derivative is ever equaling 0, okay? All right, well, could this fraction not exist? Well, sure, if the denominator equals 0, the fraction's undefined. And I think if I let t equal 0, that would create the denominator equaling 0. So in slow motion, to figure out where we don't exist, I'd set the denominator equal to 0. So I could divide both sides by 3. And to get rid of a cube root, I could cube both sides, but I get t equals 0. So t equals 0 is only critical value. And I know the derivative at 0 does not exist. And if you remember from the first panel, if the derivative doesn't exist, that means we've got the sharpness, okay? Now, t equals 0 certainly exists. I could plug it in. If I plug in t equals 0 to the original function, I get 0 squared, which is 0. The cube root of 0 is still 0 minus 4. So the graph exists at t equals 0, but its derivative doesn't, which means we've got some kind of a sharp behavior happening. Okay, step 2. Let's figure out the intervals where we're increasing and decreasing. As before, I'm going to plot my critical value. I've only got one. That creates 2 intervals. And on each interval, g is always increasing or it's always decreasing. It can't switch because the only place it could possibly switch is right here at the critical value. So I'm just going to test each interval by grabbing a number inside of it, let's say -1 for the first interval, and giving it to the derivative, okay? So there's the derivative. So I got 2 over 3 times the cube root of -1, okay? All right, well, cube roots can handle negative numbers. The cube root of -1 is just -1, okay? So I think I have 2 over -3. And again, I don't care what the value is. That just means it's negative, okay? So I know that g is decreasing on this interval. Its graph is heading down, right? Let's test this interval. Grab a number inside it greater than 0. So let's do 1. Plug it into the first derivative. So I have 2 over the cube root of 1. Whoops, lost something. 3 times the cube root of 1. Cube root of 1 is 1, so I think this is just 2/3. And I don't care what the value is, just that it's greater than 0. Okay, so here I know that g is increasing because it had a positive derivative. So the graph was heading up, right? And at 0, I knew we had a sharp behavior because the derivative was not defined. Cool. So I have a very simple graph. I decrease, I'm sharp, I increase. So let's plot that critical value. So I've got t, I've got g of t. This was the original cube root t squared minus 4. I'm going to plot t equals 0. So if I plug in 0, 0 squared is 0. The cube root of 0 is 0. So all that 0 minus 4 is a -4. Okay. All right. So the graph. 1, 2, 3, 4. Plot my critical point. I know I'm decreasing until I get to my critical point. I know I'm increasing after, and I know I'm sharp right at my critical point. So I'm thinking I'm doing something sharp. So there's a rough graph of G. Now, could I figure out my t-intercepts? Yes, I could. Could I figure out where my y-intercept is? Well, I already know it's at 0, -4. So I could add more detail to this, but for now, this is good. And I could also say that G is increasing on the interval from 0 to infinity. And I know that G is decreasing on the interval from -infinity to 0. Okay. All right. Now, day 2, we're going to try and add in the curvature, which we'll call concavity, to get a slightly better view of what this graph is looking like.